Good morning. So I don't know if this is working. I'm trying to record it, but it's probably not very optimal. But anyway, so I will start doing a little bit from Riemann integrals, and then we go to derivatives, and then come back if we have time to these notes again. Otherwise, you have to study it on your own. Yes? Okay, so this is one of the theorems that is useful to know, especially for the coming example after that. So if you have a non-negative function whose integral is 0, then you can conclude that the function is identically 0. Okay, so that's what we want to show. Because yesterday we showed that if a function is non-negative on a given interval and it is integrable, then its integral is guaranteed to be non-negative. But now we want to somehow prove this the other way around. Okay, so what we have here is yes?
Is it possible to turn off the light?
I am not very much in this one.
Oh.
Yes. That's good. I can also see that. Thank you. Okay, so what we know is that a function is greater than or equal to 0. So we know that. So this is 12.17. So we know that for every x in the closed interval from a to b, I know that f of x is non-negative. And then we also know that the integral of f from a to b is 0. But we also know that f is continuous. Isn't it mentioned? Oh, yes. So f is a continuous function. So, and then yesterday we learned that if it is continuous, it is guaranteed to be integrable as well. And now the integral is 0. What we want to conclude, that for all x in a and b, f of x is indeed equal to 0. So if I have a non-negative continuous function whose Riemann integral is 0, that function has to be the 0 function. We want to prove this. Okay, so in principle, I can consider my 3 cases. One case, I have to show that for every x that I choose from this, f of x is 0. The argument will be slightly different. If x is a, I have to prove that f of a is 0. If x is b, I have to prove that f of b is 0. And of course, the majority of work is that if x is within the interval, I want to show that for all of them, f is 0. So I will only do that one. You can read the notes for the other ones. So I would say let P belongs to A and B. We prove that f of P is equal to 0. Okay, I want to show that for every element from this interval, f acting on that is 0. I have to consider 3 cases: if x is equal to a, if x is equal to b, or if x is in the interior. So I am doing the interior one. So there are infinitely many points in the interior. I want to show that whatever you choose in the interior of the interval, f of p is equal to 0. So we prove by contradiction. If not, then what happens to f of p? F of p becomes positive. Why? Because you told me that f always is non-negative. If f of p is not equal to 0, it cannot be less than 0 because by assumption my function is always non-negative. So the only option left is that f of p is greater than 0. Yes? So if I want to draw a picture here for you. So what do we have? So let us say here is A, here is B, and I have picked an element P within the interior of this interval. So let us say this is my P. I want to prove that f of P is 0. In other words, I want to show that the graph of the function is identically 0 here. Okay. But if you don't agree with me, then you have to agree that f of p is greater than 0. So let us say that f of p is greater than 0 somewhere here. Okay, but you also told me that f is continuous. It means that it is continuous at p as well. So f belongs to the continuous functions a and b. So this means that f is continuous at p. When it is continuous at p, according to the definition, what can I conclude? I can conclude the existence of the delta such that if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than any epsilon, positive epsilon that you give me. Okay? But I want to choose my epsilon, you will see why, to be this. First of all, can I choose fp over 2 as my epsilon? Yes, because f of p, if you don't agree with me, you have to agree that f of p is positive. Then it means f of p over 2 is also positive. So it can play the role of the epsilon. But why this epsilon is beneficial, you have to wait and see. Okay? But this is the definition of continuity at point P. Okay? So the existence of such a delta that this implies that is guaranteed. But I want to write something here. If this delta, because when you write x minus p is less than delta, it means that x belongs to p minus delta up to p plus delta. That's the meaning, yes? It is in this neighborhood. If delta is such that this interval is already small, so that the whole interval is within this interval, I don't need to change anything. But if the delta is bigger around that, so if the delta is bigger and somehow I go outside the interval, I can make that delta smaller. So I want to write something here so that if this happens, x belongs to a and b and this. Without this is just a definition of continuity. If the delta that I accidentally get is so small that everything is also inside a and b, that is okay. If not, I squeeze it a little bit more so that it guarantees this one as well. Understandable? Okay, now let us see why this epsilon works. I want to start from here. F of x minus f of p is less than f of p over 2. Do you agree that I can conclude that f of x minus f of p is greater than minus f of p over 2? Do you agree with that? Because if the absolute value is less than a number, that number is sandwiched between this number and its opposite. So this number is greater than minus f of p over 2 and less than f of p over 2. So this means that from here I can conclude this one. Yes? And then I move this one to the other side, so what happens? If I move it to the other side, f of p minus f of p over 2 becomes f of p over 2, and then you know that this is positive. Why is positive? Because f of p, according to you, it should be positive. So what does it mean? It means that I can find a delta around p so that it is first of all inside my interval, and for every x in that neighborhood, f of x is positive. So in other words, if you want to see what happens, and by the way, it's extremely intuitively clear. If you have a continuous function, okay, so it means that you have a little bit of graph around that. Okay, and if you have a little bit of graph around that, and if f of p is positive, because it is continuous, it cannot suddenly become negative. It has to remain positive around that point. That's the meaning of this is rigorous way of saying that. So this means that if this is my p minus delta, and this is my p plus delta. So that is why intuitively it was very clear, if f of p is positive and the function is continuous, it means it remains continuous close to the point, because the function is continuous and it suddenly cannot jump to the negative values, yes? But if you want to prove it rigorously, this is the case. So it means that I was able to find the delta so that it guarantees this and guarantees that. Is that right? Okay, now I start with this given one. The other assumption is that 0 is integral from a to b f. Yes? But yesterday the last theorem is that I can break this into some pieces. Instead of going from a to b directly, I go from a to p minus delta, then I go from p minus delta to p plus delta, and then I go from p plus delta to... So is that understandable? So I have broken this into 3 pieces. But what type of number is this one? Yesterday we had this. F is non-negative on the whole interval. So this, according to the theorem we have, this is non-negative. And the same is true here. F is non-negative, so this number is also non-negative. Okay, but look, within this interval, I know something better. I know, of course, it is still non-negative. If I say it is greater than 0, it is not wrong, but I do not have contradiction, because 0 becomes greater than or equal to 0, which is not a contradiction. I'm seeking a contradiction, okay? So I want to do something better. Here it is non-negative, here it is non-negative. So let me make it a little bit simpler. Do you agree that I can write this to be like this? Do you agree with that one? This is non-negative, this is non-negative. I am adding 2 non-negative numbers to a number. So definitely the left-hand side is greater than or equal to this number. Yes? But on this interval, I know that f of x is greater than f of p. We don't need to have that 0. So this means that this is greater than or equal to the integral yes? Because this function is always greater than that one. Be careful, this is a constant. But the integral of a constant can be done immediately. Do you remember we had this before? Integral from a to b of a constant is equal to c times b minus a. So this becomes the constant times the upper limit minus the lower limit. But then this p and that p are gone, so this becomes 2 delta, 2 and 2 are cancelled. And I get this. Okay? But this is a contradiction. Why? Why this is a contradiction? Because you look, 0 is equal to this, is greater than or equal to this, greater than or equal to this. But this one is positive. Is strictly positive, because f of p is strictly positive, delta is strictly positive, so the product is strictly positive. So this means 0 should be strictly positive, which is a contradiction. Is that right? Okay. So this is a good theorem to know, but of course you can do this. You need to do 2 more things, but probably in the notes I have written it in a way that it covers all cases. So this means that I have to prove the same scenario is true for f of a. I have to prove that f of a is 0 and f of b is 0. If I remember correctly, if I haven't done any mistakes, I have written the argument in a way that it covers all cases. But this is the idea behind it. Is that clear? Okay, why was it important? Because there was one example I want you to know, and this is this example. This is a metric on the set of all continuous functions. So just I want to explain it a little bit. We don't have time to go through all the details. So what do I have? We know that a is less than b, and we know that I am looking for all continuous functions. okay, on the interval from A and B. My claim is that this function defined from C, A and B cross C, A and B to R, defined in this way, d, f, and g is equal to the integral from a to b absolute value of f of minus g, is a metric on this space. First of all, does it make sense? Do you remember a metric on a set is a function that takes two elements from the set from you and gives you back positive and non-negative number. So, do you think I am respecting all these conditions? Apparently yes, because this D takes two elements from my set. Elements of my sets are continuous functions on the closed interval, and it is giving back a number to me. Because when I give you these two functions, you put them here, you find the absolute value of the difference, you integrate it. If the integral exists, it gives you a number. How should I know this integral exists? There are some theorems we had before. F and g are continuous, so the difference between them is continuous. An absolute value of function is always continuous. And then we have the composition of continuous functions is a continuous function. So this is finally a continuous function. And if it is continuous, we had it yesterday, so it is integrable. So this integral exists, so it's the real number. But for metric, I need more than that. I need 4 conditions. I have to convince myself that the output is non-negative. Why it is non-negative? Exactly because of the previous theorem yesterday. Because the function is non-negative because of absolute value, so the output, if it exists, which in this case it does, it is non-negative. Okay? And for example, what are the other scenarios of a metric? So you have to prove that df and f is 0 for every. Is that right? Yes, because this becomes integral of a and b, absolute value of f of minus f. But f minus f is 0 and the integral of 0 is 0. Okay, but the hard part is there is another one. If df and g is equal to 0, we want to prove that f is equal to g. This is one of the conditions for metric. But why this is true? Why do you think this is true now? Because if df and g is equal to 0, what I can conclude according to the definition of my metric, this is equal to 0. Okay? But we know that f minus g belongs to the continuous functions, and we know that f absolute value of f of minus g is greater than or equal to 0. Exactly because of this theorem, what can I conclude? I can conclude my integrand is 0. Yes? And then it means that f is equal to g. So you see, this part is usually very simple in the other metrics we had. The hard part was the triangle inequality. But in this problem, this is the hard part, because you have to do this one first, and then using that one you can conclude this. And by the way, symmetry is very simple. If I change f and g, because of this absolute value, the minus sign will go away, so there is no problem. And what about the triangle inequality? For example, I want to write d. So let us say that I have 3 functions f, g, and h. We know that the absolute value of f minus h is less than or equal to the absolute value of f minus g plus absolute value of g minus h. Yes, this is the normal triangle inequality. And now, because we had the theorem that if one function is less than another function, and if they are both integrable, the integral of this one will also be equal, less than or equal to the integral of this expression. But the integral of a sum is the sum of integrals. Yes? And this one is just df and g plus dg and h. Yes? and this is just d f and h. So if you want, you can write d f and h is equal to this, less than that, and that word. So that's the hard part of this theorem, was actually that one. So this one was the hardest part. So this was short because we did the hard part before. Any questions? Okay, so let us stop here because this starts with derivative. We go to the derivative first now. Okay, so we want to start a little bit about differentiability and derivative. As I told you that the lectures are complete, the notes are complete, but you don't need to study all of it. So the important part will be covered in this lecture, hopefully. Okay, so that is what you already know from your calculus. So I'm counting on your calculus knowledge, of course. So if you want to define the notion of a derivative, so let us say that I have a function defined from an interval I to R. So this would be 13.1 now. Okay, so if we have this, and let us say that P belongs to this interval, I say that this function is differentiable at P if this limit x goes to P exists. If this limit exists, we say that this function is differentiable at this point P. And what is the name of this limit? The name of the limit is the derivative of my function at P, which we denoted by f prime of P. Yes, that is what you have already seen. And of course, you might also have seen another formula for that. And probably this is this formula, which is also good to know why that is correct. For example, let me introduce a new variable h to be x minus p. And in this topic, by the way, we are only working with real functions, no metric spaces involved. Okay, so h, I will take it like this, and then I would say that if I want to change x to my new variable, so what does it mean? It means x becomes p plus h. So this limit can be written as the limit, instead of x minus p, I put h, and instead of x, I put p plus h, and minus p is just a constant. But of course, because x goes to p, it means h goes to 0. So these two formulas is useful to know, okay? Both of them the same thing. Any questions? These are something you have already seen, okay? And then we also have the notion of right and left limits, yes? Sorry, derivatives. But here, this is a little bit different because, you know, in most of the books, they will work with open intervals, but here we haven't worked with open intervals. Might be this interval is like this. Okay, and then you are unfortunate and P lies here. Okay, I don't know, B. If your interval is like this and P is one of these endpoints, you can still talk about the derivative. But in this case, this limit does not make sense if x approaches p, because when I write x approaches p, it means that x can become close to p from right or from left. But there is nothing on the left side, because the domain of my function ends at p. So if you have that situation, you need to interpret this as x goes to p from the right. If p is one endpoint, and you will still want to talk about the derivative, okay? If p is on the right side, like this, let me write it. Of course, you can include that one as well, it doesn't matter. If you have this scenario, but then you have to interpret this as the left limit. I mean, approaching to a to p from left, because on the right side, there is no function. There's nothing to define. Okay, so it's a little bit different from calculus, but if you just understand this, it doesn't matter. Of course, if P is somewhere in the middle, if here is A, here is B, and P is in the interior point, then in that case, x to P makes sense. But sometimes intentionally I want to get close to p from the right, then that will be called the right derivative at p. Okay? And sometimes I intentionally want to get close to p from the left, even though I can approach to it from both sides. In that case, I will write the left derivative. Okay? So what I'm saying is that if p is the left end point, x approaches to p should be interpreted as approaching from the right. But still you don't put plus here and say this is the right derivative, because that is the only derivative you have, so you don't need to differentiate. But if p is an interior point, then you can approach from left and from right. If you don't write anything on top of p, plus or minus, it means that you are considering approaching to p from both sides. But sometimes, even though p is an interior point, you can approach to p from both sides, but sometimes you want to tell me that no, I am approaching to p from the right hand side. Then still you put this plus on top. But in that case, this derivative is not the derivative, it's called the right side derivative, and the other one will be the left derivative. So these are conventions, these are not very important things that you need to confuse yourself about. And exactly like differentiability, so when I say that a function, again, do you remember I told you that continuity is a local property. I can talk about a function is continuous at a point. But when I say that a function is continuous and I don't specify the point for you, what do I mean? I mean the function is continuous at every point in its domain. And exactly for derivative, differentiability. I cannot say that my function is differentiable. In principle, I should say that my function is differentiable at a given point. But when I say that my function is just differentiable, it means it is differentiable at any point in its domain. But these are just standard conventions, okay? And the derivative function is the function actually whose, so let me read it for you here. So let I be a subset of R, be an interval, and suppose that f from I to R is differentiable on a set E, which is a subset of I. Then the derivative function of f on E is the function f prime from E to R. Be careful, not from I to R necessarily, defined by this rule. Let me explain it here by a very simple example. So let us talk about this function. So let us, this is not in the notes, so let me just write it here for you. I have a very simple function, you have already seen it in calculus. This function defined by f of x to be absolute value of x. Okay, so if I ask you what is the domain of your function, you will tell me the domain is R. Okay, but now my question for you is that what is the derivative function? Okay, so what is the derivative function? When you want to define a function, you have to tell me two things. You have to tell me what the domain is, and you have to tell me how it acts on the elements of the domain. So for example, this is a function. If I ask you, is this function well defined? You would say yes, because I have told you the domain, and I have told you how f acts on the elements of the domain. So this means that I have completely specified the function for you. So when I ask you find the derivative function f prime, it means the same thing. It means you need to tell me what is the domain of the derivative. So it means that what is the domain of the derivative, and for every x in the domain of the derivative, you need to tell me what is f prime of x. So be careful about the word derivative function. Okay, but what is, can you tell me in mathematical language, what is the definition of the domain of f prime? What is the meaning? It means all the elements in the domain of the function such that f is differentiable at x. Yes, that's the meaning. So that's the definition of the domain of the derivative. Why it should belong to the domain? Because you see that if p is not in the domain, the formula does not make sense at all. Because I want to have this and then take the limit. In order to be able to set this up, I need to have f of p. So this means p has to be in the domain of the function. So this means that this is, if you want, I haven't written it in notes, you can write it. So the domain of the derivative is defined in that way. Okay? So the first thing I want to talk about is the domain of this function. Okay, so you know that f of x is the absolute value of x. So it means it is x if x is greater than or equal to 0. So let me write it 3 steps. Okay, and 0 if x is 0, and minus x if x is negative. Okay, so if x is positive, you know by the rules of derivative, this is 1. If x is negative, you know that the derivative is negative. Okay? But because 0 is also a point of the domain of the function, I have to ask myself, does 0 belong to df prime or not? Okay, so how should I check that? I have to go to the definition. So I have to ask myself, what can I say about f prime of 0? So this becomes the limit of f of x, which is absolute value of x, minus f of 0, which is 0, divided by x minus 0, x goes to 0. So this is a very simple task, yes? You have seen it in calculus. So what do you say about this limit? What is this limit? This limit does not exist, yes? Because if x approaches to 0 from the right, the limit becomes 1. If x approaches to 0 from the left, the limit becomes minus 1. So this does not exist. So what does it mean? It means that f is not differentiable at x equals to 0. So now, after all these simple calculations, can you finally tell me what is df prime? It is defined for positive values, it is defined for negative values, but this is not defined for 0. So can you tell me what is df prime? Df prime is the set of all numbers except 0. Okay? But if I want to write it in the exam, I would prefer to write it in this form. So if you want to answer this question, what is the derivative function now? The derivative function, I would say f prime is a function defined from r minus 0 to r. F prime of x is equal to 1 if x is positive, minus 1 if x is negative. So it is important when they talk about the derivative function, they are also asking you about the domain of the derivative, which is the definition. So this example, I don't know if I have done it in the notes or because this is absent from here. I want to go to this one. Okay, any questions? Okay, so the problem is that we have to clean the board now because then we will not see. More or less a good example. Okay, is the question clear? A function is given. We want to show that this function is differentiable at 0. And we want to show that the derivative function, according to what I described here for you, is not continuous at 0. Okay, so how should we do? The first task is very simple because they have talked about differentiability at 0. Okay, so it means that I start with the definition. So I would say that let us calculate this limit. In principle, I am not allowed to write f prime of 0 before guaranteeing that the derivative exists. So let me start with the limit. The limit of, because I want to choose my point to be 0, so it becomes f of x minus f of 0 divided by x minus 0, x goes to 0. Yes? I am in technically speaking, sometimes I myself become sloppy and I start with f prime of 0. But f prime of 0 makes sense if after calculation I realize that yes, it is differentiable. So I start with this limit to see how it works. Okay, so help me to do that. So it becomes the limit. The denominator is just simply x goes to 0. So what is f of 0? It has defined to be 0. And f of x, when x goes to 0, you know that when x approaches to 0, as you learned in the limits, x is not equal to 0. This is guaranteed by this symbol. So if x is guaranteed not to be equal to 0, it means that I have to use this rule for f of x. Okay? And then let me simplify that. This is 0 and 1x cancel that x. And this cancellation is safe because x is not 0. So what is this limit now? This is also a very famous calculus limit. Of course, technically speaking, you have to use a squeezing theorem, yes? So you would say that absolute value of x sine 1 over x is less than or equal to absolute value of x greater than equal to 0. Yes? Because the absolute value cannot be negative and sine is maximally 1. So this product cannot go beyond absolute value of x itself. But then this limit goes to 0 when x goes to 0, because I am sending x to 0, and this is also a constant, of course it goes to 0. Then it means that the limit of the middle one is 0. But there is a theorem, I don't know if I haven't written it, but this is very famous in calculus. If the limit of absolute value is 0, only 0. The limit of the function is also 0. Okay, only 0. If the limit of absolute value is 1, I cannot say anything about it. But if the limit of the absolute value is 0, then the limit of the function is also 0. So this means that finally this is 0. Okay, so now I am safe. If I ask you what is f prime of 0, what is your answer? F prime of 0 is 0 now, because I now calculated it. Okay, but I want to know that the derivative function is not continuous. So the function, by the way, can I say that the function is differentiable everywhere now, even though I checked it only for 0? There are some theorems from calculus I'm taking it for granted. If x is 0, I manually checked it and it was differentiable. If x is not equal to 0, then why this function is differentiable based on what you learned in calculus? If x is not 0.
It's continuous.
What?
It's continuous.
No, continuity does not imply differentiability. The other way around is true. Differentiability guarantees continuity. And by the way, is this continuous? Is it continuous or not? Yes or no? Don't look away. So is this continuous or not? Yes or no? It is continuous. Yes? Because if I take the limit of what is the meaning of continuity? We studied that. The limit of f of x, x goes to 0, should be equal to f of 0. So f of 0 is 0, but what is the limit of this function when x goes to 0? When x goes to 0, it means that x is close to 0 but not equal to 0, so I use this rule. Exactly using the same argument, but instead of having x, you will have x squared. You use a squeezing theorem that the limit becomes 0. So this means that the limit of f of x is indeed equal. So this is continuous. By why this is differentiable? Everywhere. It was differentiable at 0. But for example, is this differentiable at 1? Is this differentiable at -7? Why? Because this function is differentiable. You have this before. What is the derivative? Is 2x everywhere. And this function is also differentiable everywhere if x is not 0. The only thing that makes problem for me is x equals to 0, which is excluded. So 1 over x is differentiable if x is not 0. Sine function is differentiable. The composition of two differentiable functions is differentiable, and the product of differentiable functions are also differentiable. So this means that finally this function is differentiable. So anyway, this function is differentiable everywhere. Okay? And it is continuous everywhere. Okay? But this is a good example. We want to show that the derivative function might not be continuous. So that in order to do that, I have to find the derivative function first. So how should I find the derivative function? So it might be I have to skip because there are many things to cover. But how can I calculate the derivative? So if x is not equal to 0, so the derivative is the derivative of this function. The product rule, the derivative of the first one times the second one itself, minus as plus the first one times the derivative of the second one. The first one is x squared. The derivative of sine becomes cosine. But because of the chain rule, I have to multiply by the derivative of 1 over x, which is minus 1 over x squared. And then if you simplify it, it becomes 2x sine 1 over x. And this one and that one are cancelled, so I get this one. So this is f prime of x. So now can you write f prime of x in the form of a function? If x is equal to 0, what was f prime of x? We calculated that it becomes 0. So if I ask you what is f prime x as a function, it becomes this expression. If x is not 0, and 0 if x is equal to 0. So this is the derivative function. So for example, if you are comfortable, you can call it a new function, g of x. And just, if you don't want to get confused, this is a new function. But this function is not continuous. Why?
Because the limit goes to -1.
No, it doesn't go to -1. The limit does not exist. The limit of this one is 0, exactly around those lines. But this is a famous one. I told you when I was teaching you, this is one of the exercises I told you to. In calculus course, you just say that it oscillates, so it doesn't approach to any limit. But in this course, we learned how to do it properly. We find two sequences that approach to 0, but the values are not approaching to the same number. Okay, so I have done it in the notes. So anyway, that was a function which was continuous everywhere and it was differentiable everywhere, but the derivative function is not continuous at 0. So it can happen. Okay? So the limit of cosine of 1 over x, x goes to 0, does not exist. I have the solution for this one for you in the yes, it was in the continuity part. In calculus, you just say that this limit does not exist. Even in that case, it was not very convincing, but anyway. Because of that, this one is 0, this one does not exist, so the limit of this difference does not exist. And when the limit does not exist, it means that the function is not continuous at that point at least. So the function is not continuous. Any questions? Okay, this is a very important theorem. Do you remember we had similar to this yesterday? The theorem told us that if the function is Riemann integrable, if the function is continuous, it is Riemann integrable. Okay? But now we say that if the function is differentiable, that is also continuous. Okay? So this is important to remember. So differentiability implies continuity, not the other way around. Be careful. Do you remember the example? Do you remember a counterexample for the converse in general? We did it on the board today, yes? F of x equals to absolute value of x. So you know the graph of this function is like this, and it is continuous everywhere. But it is not differentiable at the origin. Yes? So if continuity in general does not imply differentiability, but differentiability implies continuity. And hand wavy argument. This is not bad. To prove is not hard. So you can say that. Let us calculate this limit when x goes to a. Okay? So how can I write this? I can write, because when x approaches to a, I am on the safe side. X is not equal to a. So I can divide this by x minus a. But to compensate the change I made, I also multiply it. Okay? But can I write this limit is equal to the limit of the first one times the limit of the second one? Can I do that? Is it always true that the limit of a product is the product of limits? It is always true unless it is one of these limits does not exist. But both of them exist now. Why? Because this limit is a polynomial limit, it is 0. But how should I know that this limit exists? Because you have granted differentiability. When you say it is differentiable, it is guaranteed that this limit exists, and it is a number. Yes, it exists. So this is valid. So now this one multiplied by 0 is equal to 0. So this means that this limit is equal to 0. Okay, then it means the limit of f of x becomes what? Is f of a. And this means my function is continuous at a. Yes? So if my function is differentiable at a, I was able to show that this also holds, which means f is also continuous at a. Any questions? So remember, this is an important fact. So differentiability implies continuity, but continuity implies integrability. So can I say differentiability implies integrability? Yes. Differentiability implies continuity today. Yesterday, continuity implies integrability. So differentiability also implies integrability. Okay? Okay, so now let us go to this one. This is, I just want to intuitively talk about that, and then we stop for a short break. So this is interior extremum theorem. So you have seen this in the calculus, local extreme point, local minimum point, so you know about those. So let me describe it here for you a little bit. So what is a local maximum? Do you remember something from your calculus course? So for example, if I have this function, yes, this point is not, of course, the highest point, but it is called a local maximum point, yes? It is not the highest, because, for example, this point is at a higher level. So I cannot say this is the maximum of my function. No, that's a lie, because this function goes beyond that, okay? But this is locally maximum. It means that if you compare it with the height of the points in the vicinity, that point is higher. So that's the motion of the local maximum. And this one, for example, is also a local minimum. So intuitively, can I say that if I have a local maximum, so let us say that this is C. Can I say that f prime of C is 0 always? In this picture it is, because if I draw the tangent line here, the tangent line is horizontal, so the slope is 0, and the slope is the derivative. So we already know that in this case it is true. But can I claim that whenever I have a local maximum, the derivative at that point is 0? So intuitively, can you draw a picture that's not the case? For example, if I have this point, yes, like that. Is this point a local maximum? Yes, because it is higher than the point in the vicinity. But if I say that this is C, can I say that f prime of C is equal to 0? What is that? What is the correct one? Yes?
It's undefined.
It's undefined. It does not exist. At sharp points, the derivative does not exist because the left derivative and the right derivative are different. So, but these are the only situations. If you are at a local maximum, okay, and the derivative exists at that point, then it has to be equal to 0. Is that clear? But there are also some, in this case, we have intervals. Usually in all analysis books, so if I have an interval, let us say that I am from here to here, and this is the graph of my function. So it starts from here and goes here. So is this point a local maximum? Yeah, it is. Because of course there is nothing on the left to compare, but if you can compare, it is higher. So it's a local maximum again. But can I say that the derivative there is 0? Can I say f prime of a is 0? Of course not. Yes? So this is important, that this is why in this theorem it is called interior extremum theorem. Okay, so let me read it for you. So let I be a subset of R, be an interval, and let our function be defined on the interval I. If f has a local extremum, when I say extremum, it means either maximum or minimum, both of them can work. At an interior, I have forgotten to write that in red, at an interior point P of I, and f is differentiable, then f prime of P should be equal to 0. So if you want to write the derivative is 0, so first of all, the point should be an interior point. But even interior point is not completely good, because if I have a sharp point interior, the derivative does not exist, so we cannot say it is 0. So if it is an interior extremum point, and if it is interior and the derivative exists, then the derivative is 0. Okay? So this is something intuitively I think is enough for us. Let us see what we have here. Yes, let us have a break and then continue with this part.